All right. Hello, everyone. My name is Jitendra Pandey. I work at Hortonworks. I'm engineering manager for HDFS team, and I also write code. I'm a member of Apache Software Foundation. I have been working on Hadoop for since 2009, and I've been involved with Ambari and Hive as well. So the outline of the talk, we'll talk about some introduction into what Ozone is and what an object store is, and I'll spend some time talking about how Ozone fits into the scheme of HDFS, and then I'll go into details of Ozone architecture, and I'll conclude the talk with some implementation aspects about Ozone. In the end, we'll have some questions. So if you look at the storage in Hadoop ecosystem, file system is HDFS. It's used in many different use cases. We have a SQL database, Hive. We have a NoSQL database, HBase as well. But we are missing an object store. And there are many use cases where an object store is really a requirement. If we compare it with what a file system offers versus object store, the two key things come out is an object store scales a lot more. The reason is primarily because the semantics it offers are much simpler. The semantics of the file system are a lot more complicated. And because of that, it's very common to see object stores scaling to trillions of objects. And the object sizes that we see typically in object stores are a lot more varied. In HDFS, large objects, large files work well, but for very small files, it runs into some scalability concerns. So what is Ozone? Ozone is just an object store by what we understand by an object store, as something where you can put the data, get the data. It offers REST APIs as the primary access mechanism, durability, reliability, high scalability, security, and high availability. They are the common cornerstones of any object store. So what would Ozone really look like? If we compare it with other public clouds like S3 and or Windows Azure, Ozone URL will look like a host and port authority followed by a volume, a bucket, and a key. And S3 has only a bucket and a key. There's no notion of volume there. And Windows Azure URL, we see some notion of account. Now, Ozone looks very similar to Azure here, but there are some subtle differences, but many commonalities. So I'll talk about the concept of volume. So this notion of storage volume that we are introducing is very similar to an account in the sense that it is an admin created entity which provides admin certain controls about the usage of object store. Like some quota can be set on top of it. And it is managed only by admins. The reason we are having this bucket as well as this volume is because bucket is something that is created by users. To take a simple example, suppose I'm working on a project and I need to put some data somewhere. I go to an admin creates a storage volume for me. And now I am the owner of the volume. I can create buckets. I can provide ACLs on the bucket, and I can decide who writes to those buckets and everything. But admin controls that how I'm using the object store. So that is the reason behind this two levels of volume versus bucket. Now, bucket is a common notion as we see in S3 and in Azure as well, consists of keys and objects. Keys, we know they have to be unique in a bucket, and objects are just the values associated with the keys. One thing to note here, as compared to S3, S3 has globally unique bucket names, but Azure doesn't have that limitation, and we are not having that limitation as well. The basic access API we are talking about is REST API. This is also very similar to what most other object stores offer. We have post and put. Post at the, API can be divided at the volume level, at the bucket level, and at the key level. A post at the volume and bucket level is about the creations, and there are authorization checks as well. Then we have put APIs to update any properties associated with the buckets and volumes, and get APIs is normal get about listing, delete APIs, and the key level put, get, and delete are with the common, usually understood semantics. Now, how do we store these buckets, these keys and values across the cluster? So we are introducing a notion of storage container. A bucket can be pretty big. So now it has to be, it cannot fit in a single node. So we have to partition it into set of keys. I mean, a popular mechanisms of horizontal sharding that we often see. So that is the notion of bucket partition. Now, so bucket consists of bucket partitions where each partition has a set of keys and some associated metadata. And all this data has to be stored on the cluster. And here we are introducing a notion of a storage container. And this container is a unit of replication. It can store multiple objects within it, and it is replicated on multiple data nodes for reliability, and the replicas have to be kept consistent. So this is one of the key cornerstones of the architecture here. So, but before I delve deeper into how all these things are implemented, I want to talk about how this fits into HDFS. So we have looked at the HDFS federated architecture of HDFS in past, and what federation introduced in HDFS is that now HDFS supports multiple namespaces. The same set of data nodes can serve multiple name nodes, and the key concept here is the notion of a block pool. Each HDFS namespace has an associated block pools, and these data nodes serve multiple block pools. So now a data node can be storing data belonging to different block pools or different namespaces which have no relation to each other. So we are taking this concept one step further. We can have a block pool dedicated to Ozone. Ozone, being a key value store, doesn't have a namespace like HDFS, a hierarchical namespace, but it still needs the containers and it needs to replicate those containers. It needs to track the location of those containers, and all those requirements are very similar to what HDFS does for data blocks. So it is natural that we can reuse this notion of block pools and extend our data nodes to support not only HDFS blocks but also Ozone containers. So in HDFS, there are a bunch of code that we will be reusing, and some new code will be added. Like I talked about reusing the notion of block pools, but there is new code, like we have to add this abstraction of storage containers, and we have to implement a new data pipeline. It's better to implement a new pipeline because the semantics are slightly different. We will get into the details of those. Now, how does this impact HDFS in terms of the future directions for HDFS? So we have seen there have been a lot of efforts on HDFS to scale it up further, so that HDFS can support billion files. Now, to this scalability, there are two aspects. One is the namespace scalability and block space scalability. No matter which solution we pick, it is important to look at them separately because the requirements there are slightly different. Yesterday there was a talk on namespace scalability, which is called partial wherein you put the part of the name node state on the disk, and this is HDFS 8286. And so that part addresses how do we scale up the hierarchical namespace. But that is independent of Ozone because Ozone does not have a hierarchical namespace per se. But there is another big aspect which is block space scalability, which is also a big part of the name node state. And therein, this similar approach of putting it on disk doesn't really work because the block space doesn't show those, exhibit these locality properties that a namespace can possibly exhibit. So, and therein, we think that Ozone can contribute there, this work that we are doing, because we are introducing a notion of containers which can have multiple objects. If we can take it further and put multiple HDFS blocks within a container, we would be able to address the block space scalability issue. This discussion is slightly orthogonal to this talk, so I will stop here. Now we get into the architecture. So there are two parts here. As we will see, I will start with the example. The key part is that given a key or a bucket name, how do we put where this key is stored and decide where this key is stored on the data nodes, and And also, how do we partition those keys, and what is the storage format in which this resides on the data node. So we will cover one by one, but at a high level, we have to follow very simple steps. You have a bucket name, and just find out where the bucket's metadata is stored, look it up, find out where the key is stored, read it up. But these finding where the location is the key part. So at a high level, everything is stored in the storage containers. Each container is identified by a unique ID. Think of an HDFS block. It is, from that perspective, it is very similar, just that it has an internal structure that we'll talk about now. Now, this mapping, instead of mapping a key to a data node location, we have a two-way, we have a hop. A key is mapped to a container ID, and a container ID is mapped to the data nodes. And the reason for this is because we have already mechanisms in HDFS to track these block locations, and that we can reuse to track container locations. So this picture is very similar to an HDFS picture. Instead of a name node, I have a storage container manager. Think of a block, HDFS's block manager here, which is maintaining a big container, a big map, where given a container ID, it can tell you which data node has this container. And how does it maintain? It connects the container reports, very similar to the block reports. It collects the heartbeats from each data node, and keeps track which data nodes are alive. So it's all very similar to how HDFS block pools work. But there is one green little thing here called ozone handler, and that is the handler that where the REST API for ozone is handled, which enforces all these authorization checks, or all the coordination between storage container manager to look up the location, and all that is done in the ozone handler. So, and I have talked about storage container manager already. So how a typical call flow would work? So I have a REST call landing onto an ozone handler, and then ozone handler will request the container location to the container manager. It has to request the container location for the bucket metadata. It has to request the container location for the respective key. Now, how does this mapping happen? I will talk about it. And then once ozone handler knows where to read the metadata from, it goes and reads the metadata from. Now it knows where the data is, so it redirects the client, and the client then reads from the respective data node where the data is. The redirect we have introduced because in certain cases the reader gets a locality. So that is the, I mean, an alternate model is that the first ozone handler can proxy it, and in HDFS actually both models exist. So we will probably have that flexibility later. So now I'll talk about some of the implementation aspects, and here two key things we have to talk about. One is how we are sharding these keys, and second is what a storage container really looks like. So mapping a key to a container, as I mentioned earlier, that all these keys need to be mapped to the container IDs. So there are two popular partitioning schemes that are used everywhere. One is hash partitioning. The advantages are that hash partition stores very minimal state, and it provides better distribution. I mean, if the hash function is good, and it's low probability that you will run into hotspots. The advantage of the range partitioning scheme is that it gives you sorted keys. Some of the operation like ordered listing becomes easier. So we plan to support both the partitioning functions. Right now we have a code for hash partitioning, but actually the implementation is very similar. So hash partitioning, the way it works is we take a hash of the key and we prefix a bucket ID to it, and that becomes my container ID. Now, not the whole thing. The container ID is essentially a longest matching prefix of this key. And why we are using this prefix mechanism is because we have to keep in mind whenever new containers are added, we will have to rehash certain keys. and we must minimize the amount of rehashing to be done. In fact, any rehashing that causes the data to move from one node to another node is going to be very inefficient, and that is why we use this prefix matching and maintain a prefix tree. That given a key, you traverse the bits and reach to the, I will have a demonstration of that. So, and as I mentioned, this to minimize this rehashing, we introduce new containers by splitting existing containers. When an existing container is filled up to its capacity, we split it into two, and only the keys within that container needs to be rehashed. And since that container is on one data node, it becomes a very local operation to do this rehashing. So this is a typical prefix matching tree that a hash partitioning scheme can use. So, and one thing to note is that we have containers dedicated for buckets, and there will be one such tree for each bucket, because having containers tied to a bucket, I mean, there are some makes it implementing security and access easier later on. So if we look at assume a key which hashes to this value in white 125, and we have a bucket IDs A, B, and we concatenate them and get a key. Now we just traverse down this route and we start from the lowest significant bit. It is the 5 goes to this path of 101 and we get to this container. One thing to I want to mention that the amount of state here has the same complexity as the number of containers in the system. So in that way, the space complexity here is very similar to what HDFS block space has. Now I'm demonstrating how we split this leftmost container out there, because suppose we want to, this container is filled up and we want to create one more container here. So we remove it and add a new trinode there, and all the keys that have the next bit as 0 go to the left side, 1 go to the right side, and you see the new container ID is again matching this prefix of 100. Range partitioning is very similar. The tree looks very similar. Instead of having a prefix tree, we have a range index tree, where each node of the tree represents a key range. The children split the key range of the parent, and the lookup is performed by just traversing down the tree, following the range in which the key falls until we hit a leaf, which is a container. So if you look at it, it is very similar, except that we have a key ranges there, and for this key we can see that it will follow the path to this container, and other properties are very similar. Its complexity is also the same. Okay, so storage container. How do we implement a storage container? Now we have, as we said, we are trying to reuse the HDFS block structure, and HDFS, therefore it is natural that we extend it in the code base. We extend the notion of the block. Now block has a block ID, has a generation stamp, and has a size. So and all these properties equally apply to the storage container as well, because we need some sort of mechanisms to maintain consistency between the replicas. Like generation stamp is a mechanism for that. Of course, we need an ID, and this so all that storage container inherits all that from the block, but we will introduce some structure underneath. But a note on the container size. In HDFS, we have seen that the HDFS blocks are typically, I mean, in many installations, we have seen something like 256 MB block size or 128 MB block size. But the size of the block really depends on the files, what is the sizes of the files, because each block has data for only one file. And we often see that for small files, the blocks tend to be much smaller than the configured block size. And therefore, the real block size on the cluster is the property of the data and not really property of the system. And that's where, since each block is tracked in the name node's memory, the state of the very small blocks become a bottleneck, because then for the same number of blocks, the amount of storage that name node is managing becomes smaller. With this notion of a storage container, which has multiple objects within a block, we don't run into this limitation, because we can always make sure that a container is filled up to its configured size. Now, there is a trade-off, what size to pick. We want a large size because that means that the amount of state required to store the same amount of storage in the central container map is smaller. But at the same time, a very large container means the cost of replication is higher. It will take longer to replicate. In some cases, this cost is more important when we are actively writing to the pipeline and the pipeline breaks, and we have to make sure that there are 3 replicas in the pipeline. We have to recruit a new block. So at that point, how much you pause in the pipeline, those details are very important. That is why this size, there is a trade-off here that we have to carefully pick. So what do we need from a storage container? A storage container has to efficiently be able to give us the data. We should be able to put and get, we should be able to list. But there are some more, the requirements actually depend on what kind of data is being stored. If you look at the metadata, we have to store, say, bucket ACLs. The unit of data is very small. We have to store just a few kilobytes of data probably per bucket. And for those ACLs, it is very important to support atomic update because they will be modified, they will be frequently modified. But the API is probably good, get and put is sufficient here. But if you look at object data, which is a lot more varied in the range, that produces different kind of requirements. And here, for object data, atomic update is not requirement, not really important, because update is in-place update is not really needed in many systems. But for object data, we have to provide a streaming API because many use cases need, and particularly also a get put stops making sense for larger objects. So for these variety of requirements, we are looking at some of the popular single node object stores. So one choice comes out is this RocksDB, which is an embeddable key value store. It is written in C++, but it provides Java binding as well. And but this is on a single node, and we will have to build replication on top of it. Now the replication is needed. We need a live replication there, in the sense that have an active pipeline which is writing to each. Like in HDFS blocks, we have a pipeline where we write to one block and that is relayed to the next block, and similar pipeline we have to build on top of this container implementation as well. And one of the key design requirements here is that in case there is a pipeline failure and now we pull in a new container into the pipeline, we have to make sure that this new container matches the state of the existing containers, and that will need some sort of live replication. RocksDB provides us snapshots and incremental backups, so which is also make it a good choice. Then also since we have very wide variety of object sizes here, the implementation we are looking at will be some sort of hybrid, that for small objects we put it directly in the RocksDB, but for large objects we can put only the file path in the RocksDB while the individual object is in a separate file. But this whole will be within a container. So this is the key difference from an HDFS block, that now the block is not just a sequence of bytes. This is there is a more structure here. But at the same time, still the pipeline semantics has to be built on top of it, and it has to provide the same consistency guarantees and what HDFS offers. So what are the guarantees that we will need from this container? When we put data, at some point we have to guarantee that the data is visible. So for that we need some sort of transactions. Now RocksDB provides us transactions, and in fact most of the embeddable stores, all these like RocksDB is a derivative of LevelDB, so that offers transactions. Now there are 3 important transactions. Commit is very important because when the data is being written to the pipeline, at some point data has to be made visible, and the commit operation basically promotes it to the visibility status, and after that the container guarantees that this data will be there. And put operation is useful for a small object, for metadata, and of course we need a delete. And this notion of transaction is also important and useful to ensure that the consistency of the pipeline, and we will use it for the consistency. So how does HDFS offer consistency? There are two important notions in HDFS. One is the generation stamp. When the pipeline is running, it has an associated generation stamp. And whenever there's a pipeline failure, we upgrade the generation stamp so that any stale object is discarded later on. That mechanism we still need. But it is possible that there are two blocks in HDFS. There are two blocks which have same generation stamp but with different length of data. In that case, we honor the block which has a longer length. Now, if we take that to containers, in containers it's hard to have a single length of the data because there are multiple objects here. So there we use this notion of transaction ID. The container which has the more recent transaction ID is honored. Now, so these containers must persist that what are the transaction IDs that have been executed. And so when a data node starts, suppose data node was running and there was a failure and it comes back up. At that point, all the temporary data which was not committed or there was no associated transaction is discarded. So now each container synchronizes to the last committed transaction. And at that point, when it is pulled back into a pipeline, we have to make sure that it is up to date with the latest transactions and all the temporary data afterwards relate back to it. So this transaction mechanism gives us an ability to ensure consistency in the pipeline as well. Now, the correctness guarantee is just very similar to what HDFS does, that when there are two blocks, if they in the cluster and they both have same generation stamp, they have same transaction ID, then they have to be part of the same pipeline. If something is stale, it is discarded or fixed to catch up. Now, since RocksDB offers this notion of transactions and snapshots, it is possible that if a container is stale and it is lagging behind, then it can be fixed by relaying the additional transactions to this one. All right, so we have work is going on. HDFS 7240 is the JIRA number. And in the first phase, we will implement the basic API and all this mechanism that we talked about. In the later phase, we introduce high availability and security and multi-part upload to support lot bigger sizes. So a note about high availability, we have, since we are building in HDFS, we can reuse lot of experience from HDFS to build in these requirements, these features. Like for high availability, there are two choices. We can use a just general node mechanism that HDFS already has, but there are other choices like using a Paxos cluster and all, but we will get there in phase 2. Security, HDFS has a full mechanism of using Kerberos, and most likely we'll end up using that. And but from the authorization header semantics, we are trying to closely follow what S3 does. And there are other features like we do want to improve later. Many of this data that we're talking about, for example, bucket associated metadata or bucket IDs, they can be cached, and this caching layer will build on top. Okay, let me introduce my team. We have Anu, engineer. He works at Hortonworks and has been contributing to this project and Hadoop for some time now. Arpit is a veteran in HDFS and has made a lot of contributions. Chris is also a veteran, and Arpit and Chris are PMC members and have a lot of experience with HDFS and have made great contributions to this project. I must mention Sanjay, which most of you probably know, and Enis and Suresh. They have been very helpful in valuable suggestions and for long hours of discussions. Thank you. I am 10 minutes earlier. I will take questions. Yeah. Thank you. Yeah.
Very good presentation, Jitendra.
Thank you.
I had one question around reading an HDFS file or also an object while another transaction is kind of deleting it. So let's say you have a huge object and one transaction is kind of deleting it while other transaction was reading it. Would you allow the deletion to happen even when one guy is already reading it? So, and if that is the case, then are you gonna, basically when is the space reclaimed? Because you cannot delete it right away. So this is kind of the question.
Okay, so like RocksDB and many of these object store, they implement when you delete it puts a tombstone. So the data is still available, and data is usually reclaimed after the when the compaction kicks in. So that that compaction will be an offline mechanism.
So basically the follow-up question was, when do you reclaim that space? Is there any daemon running which is periodically checking that the last committed transaction is kind of pretty much ahead, but the log number of basically that tombstone thing is pretty old, so now it could be reclaimed. Do you have something like that? Or?
No. So this once the transaction is the delete transaction is committed, after that it can be deleted at any point. Okay, but if there is an active reader, so there is an active reader, then compaction mechanism can check that if there is an active reader, then delay it. But whenever the compaction kicks in, it will see that there is a tombstone and there is no active reader, it will just reclaim it. But after that there is no guarantee. Once the delete is committed, there is no guarantee whether data is available or not available. Yeah. So it is possible that the delete is committed and still you are able to read the data. But new readers will be denied because there is a tombstone.
The reason I asked this question is lately I was working with HDFS 2.6. So we deleted the file while another guy was reading it, and surprisingly, that another guy who was in the middle of the read, he got an error. I was expecting it to continue to read because it had opened the file.
Okay, so in HDFS,
we can talk offline about it if you want.
Just a concluding remark in HDFS. So what can happen is that when you delete, the blocks are getting reclaimed. So that block you can still have access to because that block is open to read. Right, but there are other blocks for a large file which may have been reclaimed, so it is possible in HDFS.
Yeah, this Ozone and HDFS can exist in the same data nodes, right? However, the hard disks are actually partitioned. Are they shared? Are they allocated exclusively? Or?
Okay. Okay. So right now the way HDFS Federation works in the block pools share the hard disks. They share the volumes. So a block pool can be part of the same disk. Basically, two block pools can be accessing the same disk. So that is definitely possible with Ozone. And for performance reason, we will explore how to build certain restrictions because we have to see that the too much of randomization of disk I/O needs to be avoided. But that is definitely possible, and by default, that is the case.
One more question. In your the call flow, you showed that client directly talks to Ozone handler on the data node. So any data node it can access, like what's the client's URL?
Okay. From architecturally, it can access any data node. But from security point of view, it is possible that certain data nodes are configured or designated.
Okay. Good presentation. Cool
Thank
stuff. You. So 2 questions. First, how is it, why S3 HDFS is not enough? Seems like the same semantics, right? Buckets, volumes.
Why?
S3 HDFS.
S3 file system in Hadoop.
S3 file system,
okay.
Right. That's one thing. And another, why is it, Ozone seems to, change lots of stuff in HDFS. Why is it in HDFS? Shouldn't it be a separate project?
Okay. Yeah. Actually, the answer to first question is that we deliberately want it in part of as part of HDFS. One drawback for S3 is that it is a separate public cloud, and if you want an object store in private cloud, then of course S3 is not an option. But so there is a value to put it in HDFS. The key value, the most important advantage is that which all these other object stores suffer from. If you are running MapReduce, they do not provide any locality of data, which we will be able to provide. And so in fact for Hadoop or MapReduce integration, this will be the best object store out there. And another thing is, sorry, what was the second question?
Why don't you have a Ozone as a separate project, not a part of HDFS?
Okay, yeah, so
I mean,
I think
there's some dependency, but a lot of parts are changing.
okay. So, well, the reason, so one thing is that it has to be in same code basis for the same reason that I mentioned, because we want to make sure that it is part of the same architecture, and the data nodes become a storage platform that serve not only HDFS file system but also this object store data. And the advantage is that this running MapReduce on top of an object store becomes much similar and much simpler and much more efficient than what other S3 file system can offer. So that is the key reason. And since we are reusing so much of code from HDFS, and this it so naturally fits in HDFS federation mechanism, it makes sense to have it as the same project instead of building a separate layer. And also there are advantages of manageability, and because we are introducing just one more daemon, like this is storage manager. Apart from that, it's the same data node. So from management point of view, I mean, it will be like you get two storage systems at the cost of one.
I have some questions about the security, basically two questions. One is for authentication on the REST. Do you use Spangle or Kerberos on HTTP, or what
yes,
do you use?
Yes, we will support Kerberos.
Okay, second question is about the authorization. Do you have the security or permission defined at container level or bucket level or block level?
Okay, so in first phase we are providing it at bucket level. Okay, but we are still debating. I mean, and most likely we'll extend it to the individual object level as well. The architecture doesn't really prevent it in any way.
So the permissions are associated with the bucket metadata and stored there. Okay.
Okay, so normally in HDFS, when you write a file, you lock the block in the name node. So that goes away now. In object store, you don't lock it. But the price object stores have to pay for that is that rename is a very difficult or impossible operation. Could you comment on that?
Yes. So rename is a tricky operation here, and having a atomic rename and across the buckets and all is going to be very complicated. And we are thinking of some other commit mechanisms or some other simpler mechanisms, like one particular choice is having a notion of a temporary object, where I can create a temporary object and rename to a permanent object. So these smaller choices or simpler choices we are exploring. But yeah, atomic rename will be.
We can discuss offline.
Yeah. Thank you very much.